How's it going, everybody? This is the second video from Introduction to Linear Algebra, where I am going to explain the geometry behind an inconsistent system of linear equations. By the end of this video, you're going to understand two things. First, you'll learn the Rowwise interpretation of an inconsistent system means there is no common intersection among hyperplanes. Second, you'll learn that the Columnwise interpretation of an inconsistent system means coefficient vectors are linearly dependent and are on the same line or hyperplane. However, the constant vector of the system is not on the same line or hyperplane. If you do not know what row-wise or column-wise interpretations of a system of linear equations mean, please refer to my first video in this playlist that goes over them thoroughly. I'll put a link to that video in the description section below. Let's start with the definition of an inconsistent system. An inconsistent system of linear equations means there is no solution. The word inconsistent is a fancy name for no solution. Consider 0 times x equals -8. There is no x on the real line from -infinity to +infinity satisfying this equality. We can say the left-hand side is not consistent with the right hand side. That's why we call it inconsistent. Consider this system of linear equations in R2. We need to apply row operations on the augmented matrix to determine if this is a consistent system. The augmented matrix is this matrix that has the coefficients here and has a constant vector that is on the right hand side of the equation. We need to scale the second row and reassign it to the second row again to get this line. Then we subtract row 1 from row 2. Having zeros at the last row of coefficients and having non-zero constant in the constant vector means that 0 times x plus 0 times y cannot be -2. This makes our system inconsistent. To examine the row-wise picture, consider the system as two lines like this. Divide the equations by the right-hand sides to find x-intercept and y-intercept as the denominator of x and y here. So we have -1 as the x-intercept and 1/2 as the y-intercept. Connecting them gives you the line. Similarly, we have -3 as the x-intercept and y equals 3/2 as the y-intercept for the other line. Connect them to get the line. If you draw both lines, you can see that these two lines are in parallel and there is no intersection between them. This is the row-wise interpretation of an inconsistent system in R2. Now let's look at the column-wise picture by drawing the first coefficient vector, this vector, as here, and drawing the second coefficient vector as here. If you plot them both, you can see that the two vectors that we are dealing with are on a hypothetical line, this blue line. If you plot the constant vector -1, 6 that is on the right hand side of our equation, we get this picture. Now the question is if we can use the green and the red vector to get to this point -1, 6. Let's see if we can do that. If you multiply the red vector 1, -2 by a positive number x, then you get this point. If you multiply the red vector by a negative number whose absolute value is larger than 1, you get this point right here. Similarly, if you multiply the green vector here by a positive number less than 1, that is y here, you get this point. Or if you multiply the green vector -2, 4 by a negative number, you get this point here. It does not matter what your multiplier x and y are, you are stuck on this blue line right here, and you are not able to get to this black point here using these two vectors. This is because the coefficient vectors, this one and this one, are linearly dependent and define this blue line. No matter what multiplier we pick, we cannot get to this black point -1,6, which is not on this blue line. So what is the takeaway? The takeaway is that for a system of linear equations that is inconsistent in R2, which is this system that we are dealing with, two lines as the Rowwise interpretation have no common intersection in R2, and the Columnwise interpretation means that coefficient vectors, this one and this one, are linearly dependent, and they define a line, and they are on the same line. However, the constant vector that we are dealing with is not on that same line. That's why we have no solution. Now consider a system of linear equations in R3. We want to see if this system is inconsistent or not. To do that, we first create the augmented matrix. Then we swap the first row and the second row because we have 0 in the first row when we start with the augmented matrix. Now we subtract 3 times of R1 from R3 to make the first element 0 in the third line. Then we scale by -1/2 to get this line, and subtract R2 from R3 to get the last line. 0 in the coefficient matrix on the last row with non-zero -1 on the constant column here means that there is no solution to this system, and this system is inconsistent because we cannot have 0 times x, 0 times y, 0 times z equal to -1. Now that we know our system is inconsistent, we can take a look at Drawwise interpretation by plotting the first pair of two hyperplanes, red and green one in this picture. You can see that we have intersection over here. Similarly, this picture is the plot of pair of purple and the red one. And the last pair is the purple one and the green one here. Finally, if you plot all the three simultaneously, you can see that there is no common intersection point among all three. That is why we have inconsistent system. Now consider the column-wise interpretation in R3 for the previous system that we were dealing with. By looking at the system, we can get these coefficient vectors. For example, we have 0 times x plus y, so we have 0, 1, 3, and 0, 1, 3 is going to be here. And similarly, we have 1, 3, 7, so we have 1, 3, 7 here. We want to find x, y, z such that this vector equality holds. Our first coefficient vector is this red one vector. The second vector we're dealing with is the one that is in orange here. The third and the last coefficient vector is this vector, which is in blue over here. And finally, the constant vector -5 to 6 is this purple vector that is on this coordinate system. But this picture does not show everything that is going on under the hood. So I am going to rotate this system so that you can see it clearly. This picture shows that all three coefficient vectors that we have are on one hyperplane. Let me plot the hyperplane so that you can see it clearly. This black line here is the hyperplane on which all the coefficient vectors are located. This means that all these coefficient vectors are linearly dependent since they are on the same hyperplane. Let me show you that hyperplane which is in green color. You can see coefficient vectors are on this hyperplane, but the constant vector that we have, this vector, it is not on that hyperplane. That is why we have no solution, and that is why this system is inconsistent. Let's recap. Rowwise interpretation of inconsistency in R2 means that we have two parallel lines that do not coincide. Columnwise interpretation of inconsistency in R2 means coefficient vectors are linearly dependent. That means they are located on a line, but our constant vector is not on that line. Rowwise interpretation of inconsistency in R3 means three hyperplanes have no common point. In other words, they do not intersect at the same point. Columnwise interpretation of inconsistency in R3 means coefficient vectors are linearly dependent and they are located on a hyperplane, but the constant vector is not located on that hyperplane. Now you can keep this picture in your mind to remember both row-wise and column-wise interpretations of an inconsistent system. With that being said, I'll finish the video. Thank you for watching my videos and I hope you've enjoyed this video. There are two things you can do to support me. You can support me by liking my videos and giving them a thumbs up. Also, you can share my videos with anyone who you think would find them useful. Finally, please make sure to subscribe to my channel to get notifications for new videos and have a great day.